Graphs always have a basic form in their home position. Y equals x squared, y equals x to the third, y equals the absolute value of x, y equals the square root of x, and y equals the cube root of x. They are all in their home positions. Notice that all of them are centered around the point 0, 0, which is called the origin. This is what they look like if you don't do anything to them. Now we are going to proceed to talk about the kind of computer coding, which is what transformations is like. Yes. How we're going to do it and how we're going to move these little guys and change their shapes. Okay, let's look at a general function. All functions are made up of parts that are part of the argument, and that's the most important part. That's where the x is. Wherever the x is, that's the argument of the function. And then every other place in front and behind the argument, that's not the argument. So all functions are divided up into the argument part where the x is and the not argument part where the x is not. The argument part governs the movement of the sideways movement, the horizontal movement of the graph. And they do that by affecting what the x coordinates equal. The not argument parts affect the y coordinates of all the points and what they equal. So the argument is where the x is. Every number in the argument affects horizontal movement, horizontal left and right. Every number on the outside of the argument, both in front and behind, affects the vertical movement. We're going to be working with these 4 functions today, just because it takes too much time to work with all of them. We're going to be working with f of x equals x squared, g of x equals the absolute value of x, h of x equals the square root of x, and s of x equals the cube root of x, just to get you familiar with all this. And what that does is we're doing two of the 3, and probably that's all we're going to get to, the 2 transformation homework sets that you have for today. All right, so let's talk about the vertical movement first, because that's the easiest and the most straightforward. If you want to take any of these graphs and move them directly up or directly down, governed by the far right end of the function, the part that's outside the argument over on the right. So if you want to shift x squared, f of x equals x squared, or g of x equals the absolute value of x, these 2 graphs in their home positions, if you want to shift them vertically up, this is how you would code it. If I want to shift y equals x squared up 3 units, I would just put a +3 on the right end. That's it. Not hard. If I want to move the absolute value of x up a certain number of units, like 5 units, then I would put a plus 5 on the far right end. Always on the right end, always added or subtracted. But for vertical shift up, you're going to put a plus. Now, before we go over here and talk about down, let's talk about y equals x squared and y equals the cube root of x. Okay, we've got h of x equals the square root of x. If I want to move that up, physically up, this, just up 4 units, all I would do is put a plus 4 on the right end. And we're going to actually do some of this with the graphing calculator. And if I want to shift the cube root of x up 2 units, I just put a plus 2. Right end, outside the argument, like these are. All vertical movement takes place by coding outside the argument. So we are not in the argument at all right now. If I want to move y equals x squared down 3 units, I would put a minus 3 out here, not negative 3, but subtract minus 3. So x squared minus 3 would take x squared down 3 units. And absolute value of x minus 5 would take the absolute value of x physically down 5 units. And if I wanted to move the square root of x down 4 units, then this would move down 4 units, simply by putting a minus 4 outside the radical, because this is the argument in here. In here, that's the argument. Out here is not the argument. So I say minus 4, subtract 4. And to move the cube root down 2 units, there's the cube root, I would move it down 2 units by subtracting 2, putting a minus 2, but you've got to put it over there on the right because that's where it belongs. That's where the vertical shift is. You can have a vertical shift up with a plus, or you can have a vertical shift down with a minus. That's not negative, it's a subtraction. Okay, it's as straightforward as that. Let's graph. How about this? X squared plus 3. That's what I wrote. X squared plus 3. Graph it. There you go. Now, a better way to do this, and I should have done it that way. Clear. I am going to let y equals x squared be in the home position, and it's going to be blue. There it is. Y equals x squared in its home position. Now to move it up, I'm going to add 3. I'm going to come down to y2. That's going to be red. And I will have x squared, yes, but I want to move it up 3 units, so plus 3. And then graph that. Now, if I wanted to move the blue guy down 3 units, instead of a plus, I would have put a minus 3. So x squared minus 3. That's going to be black. I haven't changed it yet. Okay, so here's y equals x squared in its home position. If I want to shift up 3, I say x squared plus 3. And if I want to shift down, I say x squared. And then away from the x squared on the right. And the same thing would be true for all of the others. But let's go through them. So clear, down, clear, and then back up. How about the absolute value of x? That's the one that's a little harder to get to. I push the math button, and then the right arrow key to go over to num. And then, yeah, I'm going to accept abs, so I hit enter. And there I have the absolute value of x. I click on x, and I come over. You want to I want to move it. Here we are in the home position. I want to move it up 5. Go down to Y2, again, math, right arrow key, enter. X. Now I have to move to the right outside the absolute value bars, or I have to make sure I've closed my parentheses. Happen out here, plus 5 rather. Now I'll graph. I have just moved this guy up 5 units. If I want to move the blue graph down 5 units, then I'll do the same thing. Here. So I'll come down to Y3 and math, right arrow, enter. Okay, and I'll put an X, and I have to come outside the absolute value bars, put a -5, graph. The -5 brought the blue graph down 5 units, and the +5 brought it up 5 units. Directly up, doesn't change anything else. Okay. Now for the square root of x. Second x squared gives me the square root sign, and x, and then right arrow key or close parentheses. There's the basic graph, centered at the origin. If I want to move this up, I forget how many I said. If I want to move this up, let's say up 2, and then I'll move down, up 4, and then I'll move down 4. Okay, I'll come down to Y2. Second x squared gives me the square root of x, and right arrow key. Or close parentheses. Very important your parentheses be closed now. I'm going to say +4. This +4 is not under the square root sign. It's outside. That's what makes the vertical movement. So what I did physically moved this blue line up 5 units or 4 units. 1, 2, 3, 4 units. Now if I want to move the blue line down 4 units, all I do is change the plus to a minus and it will go directly down. The important thing is make sure your +4 or your -4 is not inside the square root, it's outside the square root on the far right. Okay, that is the vertical shift. Pretty easy, not real hard. You can get used to it very easily. Now we're going to talk about the vertical stretch. Imagining that you've got the ears of some poor bunny and you're pulling up, making the bunny skinnier or higher, which is really what you're doing. You're making it higher. Now, get rid of this for a minute and talk about vertical stretches. We should all do our stretches. The vertical stretch has to be a number greater than 1, greater than +1. Let's make sure we're on the same page there. And where it's located, the vertical stretch is located in front of the argument. Not in the argument, but in front of. So let me move this. To make x squared higher and skinnier, I would put the 6, I could multiply any number greater than 1, and I just chose 6. And I am going to stretch the absolute value of x 5 units. Actually, this is called by a factor of 5. We're stretching by a factor of 6. We're stretching by a factor of 5. We're stretching by a factor of 7. We're stretching by a factor of 8. So let's see what this stuff would look like to give you a visual image. So what am I doing? 6, 5, 7, 8. We'll see if I can remember that. Yes, here we are. Okay. So again, x squared is our basic graph. There it is. I want to stretch x squared vertically. Multiplied by 6. The x coordinates have stayed in exactly the same place. So it's a little bit hard to see, and it is hard to see, but you're going to have to imagine this is where the point was. Now, if the x coordinate 1 stays exactly the same, but you multiply the y coordinate by 6, then it's going to go up to 6. So now the point is 1, 6. 1, 2, 3, 4, 5, 6. Right there. A little higher. Yeah. So the point here moved up here. The x coordinate is still the same. It's the y coordinate that changed. Got multiplied by 6. Which is that number right there. we're going to have the same kind of effect to a vertical stretch if we go to the absolute value of x. No, I went to math, didn't I? Yeah, okay, there we are. X, there we go. There is the absolute value of x up close and personal. We're going to stretch it by a factor of 5, which means the x coordinates stay untouched, but the y coordinates get multiplied by a 5. Here. Maybe. Okay. The y coordinates are multiplied by a bigger number than 1, a number bigger than 1, and the x coordinates stay where they are. Okay. And, okay, let's look at what the others look like because they're interesting. They don't look like this. Not even a little. All right, here's the square root of x. Now, I'm going to stretch it, not move it physically, but stretch it up by a factor of 7. So I'll have 7 square root of x. 7 times the square root of x. Graph. Again, the x coordinates have stayed where they are. The y coordinates have been multiplied by 7. And this resulted in effectively the arm getting pulled way up by what your book calls a factor of 7. And I haven't done the cube root for you. You need to know where the cube root is. We also have to use the math key for that. Number 4 is where the cube root is. So I can go down to 4, or I can just click on 4. Either way, I get that. And then I'll type x, and then I must go to the outside. I don't really have to, but you know, it's a good habit to get into. There's the basic graph of y equals the cube root of x, the third root of x. Okay. Now, okay. Now we're going to multiply the cube root of x by 8. So I come down to y2, I put my 8 in front, and then follow it immediately by the cube root of x. Wow, this guy was stretched up here, but this guy was stretched down here. If you're wondering why, pick a point like, I don't know, how about 1, 1, my favorite. If I multiply the y coordinate 1 by 8, then it goes way up here. But down here I have 1, negative 1. The y coordinate, negative 1, negative 1. The y coordinate is negative 1. If I multiply negative 1 by positive 8, then it gets sent way down there. So sometimes it's interesting trying to imagine what these will look like when the expansion affects them. The stretch. Okay, now, where there's a stretch, there has to be a shrink, right? Let's start here with the cube root of x and come down here and change 8 to 1/8. And I can do that. I'm gonna, it would just be harder. I'm just gonna clear it and do this. Let's graph the basic graph. Now, we're going to graph a shrunk version. And see, what I'm going to do is multiply all of the y coordinates by 1/8. The same process is still going on. This number multiplies the y coordinates only. So parentheses, 1 divided by 8, parentheses closed, math, 4, and then x, and come to the outside and graph it. Wow. Let's, I'm going to change the window to get more of a close-up view. Let's see. -3, that's drastic, to 3, -3 to 3. There, see, it's not flat on the x-axis, but it's just a little bit below the x-axis and a little bit above the x-axis. We shrunk it by a lot. Okay, what about we go back to x squared? Oh, I love it. There. Okay, this is our friend x squared. Yeah, I better put the window back. There's a quick way to put your window back to its home position, which is zoom, that key right there, zoom. And then go to Z standard, which is 6. And now you're back to -10 to 10, -10 to 10, which is called your home screen. We've got x squared in its home position on our home screen. Okay, well, we are about to change all that. We're going to multiply x squared by 1/6. That's going to be our vertical shrink. Okay, that's my shrink factor. There's the function. Yeah, now this is the home position, the home graph, and its y-coordinate, see this was the point 1, 1. The y-coordinate was multiplied by 1/6. If you multiply 1 by 1/6, you get 1/6. That means the y-coordinate now is 1/6, which is really difficult. It's not actually touching the x-axis, but it's really close. So what we've done is lowered both the arms here, because all of the y's got multiplied by a little fraction. That's called a vertical shrink. Best way to deal with this is to yeah, it's my answer to everything. I'm trying to come up with another answer because it's so boring, but absolutely the best way to study in the world for me is to make a bunch of flashcards and then actually force myself to read them every day. Now you're only putting one fact on each card, so how long is it going to take you to read the card? Not long at all. You could lay in bed and read the cards and put yourself to sleep that way. I have read that your brain keeps working on it. Whatever it is you read or study or think about right before you go to sleep is what your brain is going to be working on, at least for part of the night. Okay, that would be free study time. Let's do one more. Let's just do the square root of x. There it is, home position. Now we're going to shrink it. By what? 1/5. So parentheses, 1 divided by 5. Second x squared, x. Really flattened it out. Not completely, but it's really close to the x-axis now. The point that was 1, 1 is now 1, 1/5. And if I wanted to go to the trouble to change the screen, we could actually get a better view, but I don't want to. Because we have other things to do. And we need to be doing them. We need to do something I've always thought was incredible fun. Aha! The vertical stretch and shrink numbers multiply the x coordinates? No, they multiply the y coordinates. See, I knew that going back over this before I make it permanent would be a great way to do proofreading. There now. Y coordinates. That's one way to remember it. Ooh, I'm getting warmed up. Okay, now this to me is just great fun. The vertical reflection, which is also called a reflection across the x-axis, but what you're really doing is are flipped upside down. Flipping upside down. All right, all that consists of is sticking a negative sign, not a minus sign, a negative sign in front of the function, as we will see. Let's start off with x. Oh, yeah, let's start off with x squared. So x squared. Graph. Here you are. Now I'm going to turn the poor guy upside down. Oh, it's so mean of me. Right. My negative sign on the TI calculator, you have to find your own if you don't have a TI, is right there. Right there. Let me, right there. Down here. I hope you can see. Could somebody unmute themselves and tell me if you can see my cursor moving?
I can see.
Yes.
Okay, good. Good. Okay. All right, yeah. So all I'm going to do here is put that sign down here by the enter key. That's the negative sign in front of the x squared. And now the red graph is what I'm going to get. Turn that poor little guy completely upside down. And the same is going to be true for our other functions that we're working with today. Math, right arrow key, enter. The absolute value of x. Right there, we're going to turn upside down by, again, just put a negative sign in front and then all the same motions. There you go, upside down. Now, we're still just doing the vertical movements right now, but after this, we're going to be switching to horizontal movements, which are harder. They're just more difficult. They shouldn't be. We should create a new math system so that they're not. But I'm not really sure how we would do it. Okay. Yes, but we're still flipping upside down, aren't we? So, second x squared, x. Graph. There we are. That's y equals x squared in its home position, right there, over here. I'm going to put a negative sign in front of it. And that will turn this upside down. Oops. I'm gonna move it up some. Negative square root x. There, we turned it upside down. Notice it's only going vertically upside down. And then we will do the cube root. Okay, so cube root, I go to math, and then down to 4, which is where the cube root is. And here's the graph in its home position. Now I'm going to turn it upside down. Take your bets on what it's going to look like. Yeah, is that weird? This part came up here and that part came down there. That's kind of pretty. You could make it green and red and make something for Christmas. Okay, we are done with our vertical movement, but I shouldn't have turned that off. So let me get it back on. Okay, so let's go back over it. We have a vertical shift, which occurs out here to the right. Plus means you move the basic graph up. And minus means you move the the basic graph down. All it does is move directly up or down. That's what the vertical shift does. The vertical stretch multiplies the y coordinates, but it stretches vertically, it doesn't move vertically. It just stretches up. So a number greater than 1 will cause the graph to stretch up or down, but anyway, stretch greater. How do you even say that? I don't know. A vertical shrink consists of a fraction or a decimal, but it's got to be between 0 and +1. So a positive fraction or a positive decimal that's less than 1. And that shrinks it. And then sticking a negative sign in front of the function flips the graph upside down in what's called a reflection across the x-axis. Okay, now, horizontal movement. Horizontal movement was so hard for me to come to terms with when I was a student. It was just difficult. To tell the function you want it to move to the left, you add a number in the argument so that it would look like this. Now that, of course, is not what you would expect. To me, a plus means go to the right. But that's not the way it works. I will show you how to know for sure which way you're going to go. Take the argument and set it equal to 0 and solve for x. When you subtract 3 from both sides, -3, you will get x equals -3. Negative. That's your movement right there, your horizontal movement. That's what assures you you really are going to the left. Now here the argument is x plus 2. I set it equal to 0. And why 0? I'll show you. Because in the basic graph, everything is centered at 0, 0. So here you're offsetting the graph to the left or to the right. The only way to know for sure is to set x plus 2, the new location, equal to what the old location was, and see what the movement is. So -2, -2, x equals -2. 0 minus 2 is -2. Now you can see what your movement is right here, 2 to the left. So if you're willing to go to this extra step, you will quickly memorize that inside the argument, it is where your horizontal left and right movement occurs, And a +3 means go to the left. A +2 means go to the left. A +4 in the argument, which is underneath the square root, means go to the left. A +5, which is underneath the cube root radical, means go to the left. And then after a while, you can start taking shortcuts. But you really shouldn't until you prove it to yourself. So let's take these graphs and write them this way, and you can actually see what's happening. Somebody make me stop turning it off, please. Oh, that's the photo. I don't want that. So where's my calculator? There it is. Okay, clear. And clear. And let's go to x squared. Now, our home position is x squared. Graph that. There it is in blue. Now, I alter the argument, parentheses, x plus, no, might be worthwhile watching what I do, x plus 3. Parentheses closed. Now we're dealing with x squared, so I have to put a squared up there. Okay, now watch what happens to the blue graph. It's moved to the left 3 units. Directly to the left. Same exact shape, but it has shifted over to the left. Now, if I want to move to the right, to the right, yes, watch what I have to do. Parentheses, x minus, not negative, minus 3, parentheses closed, squared. Now graph. Here's the basic graph. This is parentheses x minus 3 squared. That minus 3 in the argument actually moves the graph over to the right 3 units. I thought that would kill me, okay? When I was where you're sitting, I thought, no, there's just no way. And we didn't have graphing calculators. Yeah. It was bad. Screws with your mind. But anyway, this plus sign moves that graph to the left. This minus sign moves that graph to the right. So clear. Clear. Now we're going to do that for absolute value, and you'll be able to see exactly where the argument is. So math, right, enter, x. There's the absolute value of x. There's the graph of the absolute value of x in its home position. Notice the point. That's important. It's the only one I know of that does. Okay. Now I am going to move this to the right 2 units. So I will pick math, right, enter. Now, the argument is inside the absolute value. Bars, the absolute value bars. I will have x. Now I'm moving to the left, so that's going to be a plus here. and then 2. The absolute value of x plus 2 is going to move to the left 2 units. So the blue graph of the absolute value of x is going to be moved to the left 2 units. There it goes. And if I decided I wanted to move it to the right, 3 units. I would go down here, math, right arrow, enter, x minus, that's a negative. That'll wreak havoc, minus 3. The absolute value of x minus 3 will be a black graph. You know, I could move it down to green if I wanted green. Maybe I'll do that next time. Okay, so here we have the absolute value of x shifted 3 units to the right by the minus sign, the subtraction sign. How are you feeling about this? Are you coping?
Yes.
Good.
So really, it's just about switching the signs, I guess, because usually when I'm wanting to move to the right by 2, you would go right? But in
Yeah.
this case, when you're wanting to go to the right, you're actually moving left.
Yes, in the argument, everything is backwards. It is so strange. There are things we're not going to go into in this class that would really make you say, I cannot cope with this. I couldn't cope with it. But yes, you're right. Now we're going to do one more thing in the argument, and that is have a horizontal flip across the y-axis. It's called a reflection across the y-axis. Okay. Clear, clear, clear. Okay, now. Oh, this is what I want. Okay, if you can have a vertical flip upside down, you ought to be able to have a sideways flip. And you can. Now the thing is, you're not going to see anything happen here. It's really strange, but you'll see. Okay, so x squared. We'll just do one of these. Now I'm going to flip this sideways. Parentheses, negative x, parentheses closed, squared. It's the same graph. And the reason is that this arm goes over there and this arm goes over there when you're flipping across the y-axis. So you can't tell that anything has happened. We say this has symmetry across the x-axis. Across the y-axis there. It's evenly balanced across the y-axis, and so when there's a sideways flip, all it does is cover itself. You can't see the absolute value graph either. However, you can see the square root of x. So we'll go there. Okay, so the square root of x. There it is. Now, we are going to turn this sideways. Instead of flipping it upside down, we're going to flip it sideways. Here's how. Second x squared. Now my argument has to have a negative sign in front of the x. That's the code, but it has to be in the argument. That is going to do the flipping sideways. Here's the mirror image across the y-axis. This is called a reflection across the y-axis. It was here, it flipped over here. So that's what this is all about, that negative sign in front of the x. Actually do some concept, you will see how all of this goes together. So let's get some more pages up here, just so I need to write these down. Okay, this is number 1 in your first homework, transformations. And it says, describe how the given function can be obtained from the basic graphs, then graph the function. So I'm actually going to go to the whole thing here. And then make this bigger so that you can see. We'll leave it like that for a while. This is the argument of the x squared function. It's got a -5 in there. So 5 is being subtracted from the x. This is a horizontal shift, and instead of going to the left, which is what you'd expect, it's going to go to the right 5 units. So now we have to find which of these is the right answer. Now, we have to read each one. Start with the graph of y equals whatever the basic function is, and it's going to be x squared. Shift the graph up 5 units. No. Start with the graph of y equals x squared. Shift the graph 5 units to the left. That would make sense, but no. Start with the graph of y and shift the graph 5 units to the right. Bingo! That's our answer. The other with the graph of y equals x squared. Shift the graph down 5 units down. If that were on the outside over here, yes. If you had x squared minus 5, then you would be shifting the graph of x squared down 5 units. But it's not. The -5 is in the parentheses with the x, which makes it part of the argument, which makes it part of horizontal motion in the opposite direction from what you'd expect, unless you go to the effort of saying, okay, x minus 5 equals 0, solve for that, and you'll get x equals +5, and you'll go, oh yeah, okay, it's going to go in the positive direction. Duh. Whatever it takes.
So wait, what was the answer to this one?
To the right 5. Honest. Let me pull out my paper.
I just no, I believe you because
Okay.
I would have put it, but I just wanted to make sure.
Yes. Good. Any more questions? Any more bets on what it'll be? Okay, let's do this thing. I'm going to say the answer is C, 5 units to the right. So, in here, I'm going to put x squared. And then shift the graph 5 units to the right. So I've got to check my answer. And it says yes. Now I have to graph it. Okay, now, first I have to tell it what kind of graph I'm dealing with. And the graph of something squared is going to be a parabola. This is a parabola, and it tells you this is the x squared tool. If you hover your mouse over it, it tells you what kind of tool it is. Okay, now it says click the graph. I believe you can click anywhere, because where you move that is going to be determined by how you answer over here. Now, that -5 in the argument is going to shift the graph horizontally 5 units to the right. So you have horizontal and horizontal. This says horizontal stretch or shrink, which we didn't talk about. This is horizontal shift. Okay, I am going to the right 5 units. So I move to the right where the numbers are positive. If I were going to the left, I would go to -5. But no, this is 5. If you set x minus 5 equal to 0, you would get x equals 5. That's how you come up with the right number when you're dealing horizontally. Okay, now there is no other kind of transformation going on. So I just set it, and notice that that moved the graph over here. I'm going to save, and then I'm going to check my answer. And that was right. Okay. Next question. Here we go. Now we've got these drop-down boxes. Describe how the graph of the function g of x equals 1/4 times the absolute value of x minus 7 can be obtained from the basic graph. Then graph the function. Okay. And see how the blue here is only filled in halfway? That means you're answering the first of 2 questions. So be ready. Start with the graph of h of x equals the absolute value of x. Then, you have to read the whole thing. Then, something it vertically by a factor of. The only time you see the words factor of is when you're talking about a stretch or a shrink. Okay, and here it's telling you, okay, vertically. A vertical stretch or a vertical shrink. Well, the number in front controls the vertical stretch or shrink. And when it's a fraction, you're going to have a shrink. So then shrink it vertically by a factor of 1/4. Finally, shift it units. let's look at this. Okay, so up or down. Shift it. You're going to be shifting 7 units either way you go. But a minus on the outside of the argument means what a minus is supposed to mean. Okay, and since on the outside of the argument, that deals only with vertical movement, you are going to shift this down vertically, well, down vertically, 7 units. Because I didn't see it. There it is, down 7 units. So I'm going to click on down 7. Then I'm going to check my answer. Well done. So see, you have to put these different movements together. Now we have to pick a graph, and you can always graph these in your graphing calculator, but you don't really have to. You're going to have the graph of the absolute value of X with the arms lower, so it's going to be a V, but the arms are going to be lower. So it could be this or this. And then you're shifting it down 7 units. This is the only one that goes down. So I would vote for B. Nonetheless, the safest way to do that, it was 1/4 the absolute value of X minus 7, is to graph it, there. Clear? Clear? Okay. So 1/4 times the absolute value of X would be parentheses 1 divided by 4, parentheses closed, or quite honestly, 0.25 is 1/4. If you already know that, don't worry with the parentheses and the 1/4. Just say 0.25. Math, right, enter. The absolute value of X, you've got to move to the outside to do your minus 7. Now graph that. See, there it is. That would tell you definitely which graph is correct. Where was I? Here. Okay. Now the next one, describe how the given graph can be obtained from one of the basic graphs. Okay. Now I'm going to have to make this a little smaller. All right. Start with the basic graph of f of x equals, there's the x, there's the exponent. X squared is going to be your basic graph. That's how you tell. X squared. I guess I better do a right arrow key, just in case. All right, now shift it up, down, left, right, 2 units. Okay, the 2 is in the argument, so it's going to deal with horizontal movement. So it'll be left or right. And then the plus, which should mean right, ends up meaning go left. So left 2 units. So we're going to go left 2 units and then shift it. The other shift is out here. That's a vertical shift down. Down 1 unit. Okay. Did it say correct?
Yes.
All right. Now we're going to graph it. It's an x squared problem, so I click that. I click anywhere on the screen, but now I put in what the shifts are. There's a horizontal shift and a vertical shift. So the shifts are down here. There's a vertical shift down 1, so go to -1, -1 rather. And there's a horizontal shift of 2 to the left. If you set x plus 2 equal to 0 and solve, you'll get x equals -2. So come over to the horizontal shift and go to -2. Those are the only two kinds of transformations that are occurring. So, there. Save, check.